Okay, good evening. We're going to look into an area of physics and scientific thought which involves the response to a particular problem. And the problem is a problem that we would find very interesting from the scientific perspective. It's a little bit disturbing, perhaps. It doesn't really quite make sense scientifically, but as we go along, you'll begin to sort of get the idea behind what the question is. In fact, there are really two fundamental questions which I want to address this evening. And the title of the talk is Goldilocks and the Multiverse. I'll explain what Goldilocks has to do with all of this and what the multiverse is as we go along. But we're going to look at both the science and Torah together. I've already gone over the idea of the fact that we need to be able to learn science properly, we need to be able to learn Torah properly. We've said that each time. And in this particular talk, most of what we're going to cover will be science. But that's okay, because there's going to be some Torah at the end as well. But the science will cover a very large range of different things. So number one, we're going to look back, we're going to do a little bit of revision about the idea of the Big Bang. And in fact, if you noticed in the news today, there was a discovery has been made, although it will be tested, and I'll show you one of the slides from that, about the nature of the Big Bang, and in fact, a sort of extra level of proof for part of the theory relating to the Big Bang, which I'll explain. There are two very big questions in cosmology, which I'll tell you now. One is that it appears that the entire universe is set up perfectly for the ability to create life, and particularly within our solar system, our Earth in particular, is sort of appears to be perfectly set up in order to produce life and for us to exist. That in itself is quite a remarkable thing, and quite how remarkable that is something that I'm going to try and get across to you. The other question that we're going to deal with first, in fact, is the concept of a Big Bang. That was very important, and it's a very important discovery. We'll go over where that comes from, but actually it raises a very important question. Previously to the discovery of Hubble's discovery of redshift and the fact that the universe is expanding, which implies that there was a Big Bang, there was a beginning to it, scientists thought the universe had just existed for eternity. The problem with a Big Bang is that it implies that there was a beginning to everything. And the problem with that is that in the sort of deterministic scientific world, everything has, every effect has a cause at the beginning, right? So if I take a billiard ball and I roll it on a table, that effect of it rolling had a cause that I was there to roll it. And you can trace each effect back to a certain cause. The problem is that when it comes to the universe itself, if you wind all the way back to the Big Bang, what was it that actually caused it in the first place? That's going to be the question that we're going to look at. And by looking at some of the areas of physics, vacuum state, quantum theory, what I call the stuff of nothing, we're going to try and address that particular problem. We'll also look at what we call the Goldilocks paradox, which I have mentioned before, that the Earth is set up perfectly for life. Look at the anthropic principle, multiverse theory as an answer to that, and some of the religious implications. Okay, so it all started with this gentleman. I want to know whether God had any choice in the nature of his creation. This idea is that the world itself has a set of laws. It has a set of physical laws. It is set up in a particular way. Okay, atoms are set up in a particular way. The world works in a particular way. The question that Einstein was asking is, did it have to be like that? Could it possibly be that the Earth, the world, the universe could have been made in a different way? Okay, that's an interesting philosophical question. So let's recap where all of this began. Now you're probably familiar with, because we showed this in the first series, the first lecture rather. This is a police car. It's emitting sound waves all around. Okay, so if you haven't seen this, it's probably useful just to see it quickly. Here we're observing, or we're listening to, in fact, the siren that's coming out. And these circles represent sound waves emanating out from this stationary police car. Okay? Now, what happens is, when the police car moves, these sound waves bunch up at the front, okay? And they dilate at the back. And when the police car goes past, right, if we measure the frequency of the sound as the police car goes past, okay, the frequency will stretch and therefore the pitch will go from high to low. And this is, of course, the famous Doppler effect that you're used to hearing, and if not, okay, so you can hear that dip in pitch, and that comes from the fact that those sound waves are being stretched as the police car goes past. The same, however, as we said last time, is true with visible light. So therefore, an object that emits light, as it's traveling towards us, those waves get bunched up, and it would shift the spectrum of light coming from that object towards the blue end of the spectrum. And similarly, if it was going away from us, the spectrum of light would be shifted to the red end, in the same way that you've got a high pitch at the beginning as the car is coming towards you and a low pitch at the end. It's exactly the same thing with light, slightly different, but essentially the same thing with light. Okay? So that's all recapping what we learned before. We learned about Edwin Hubble and the fact that when he looked up, he expected to see galaxies looking pretty much the same no matter where you look at them. Okay? Here's a galaxy. Rather than emitting sound waves, it's emitting light waves. And if the galaxy is stationary, when you look at it from either side, it will look exactly the same. And of course, if you have a moving galaxy, right, at this side it will look slightly blue, because these are the bunched up light waves, now at the blue end of the spectrum. And at this end, it's going to look ever so slightly red, because those sound waves are being stretched. Okay? Very, very straightforward. And what Hubble observed was that the galaxies were all shifted to the red end of the spectrum. Here are, for example, absorption lines from our sun. These absorption lines exist because of certain elements within the sun. Let's not go into too much detail. Here are the same absorption lines from a cluster of galaxies around 1 billion light years away, and you can see that they've shifted to the red end of the spectrum. Okay, and that's because that cluster of galaxies is moving away from the Earth. Okay, so Hubble's big chiddush was, well, if everything's moving away in equal directions, wherever you look in space, everything's moving away from us, that must mean that the universe is expanding, and that implies that the universe had a beginning where it started from zero. Okay? Now, that's a recap of what we did in one of the first classes. Let's now take it into a slightly different direction. What were the conditions right after the Big Bang? What was actually going on? So scientists now have a very good handle on what the universe was like just after the Big Bang. Okay, so straight after the Big Bang, we understand that the universe was incredibly hot, and there was a sort of soup of subatomic particles which all interacted very strongly with radiation. So all of these particles are just sort of jumbling around the place. Okay? It took around 380,000 years after the Big Bang for that soup to cool down enough for photons, right? That's the light particles, to be able to no longer interact with the atoms themselves, which were now electrically neutral, and they began to travel freely around. So before 380,000 years, light itself was trapped. It couldn't get through, okay? Because it was surrounded by this dense soup of subatomic particles, and it wasn't able to penetrate. After 380,000 years, light was able to penetrate through. And that light, well, it's not light as in visible light, but it was at the time. Now, after 15 billion years or so, is now picked up as what we call cosmic background radiation, okay? The famous echo of the Big Bang. Okay? This radiation spread out into space where it can still be detected as weak waves of radio frequency, and as I said, it's known as the CMB, cosmic background radiation, and it has a uniform temperature across the sky. Now, the scientists have done a lot of work trying to photograph, or essentially measure and map this cosmic background radiation, because this is essentially the sort of birth print of the universe. Okay, and I'll show you an image of it in a minute, and I'll explain exactly what it is. Okay, these guys over here basically discovered it by accident. They were using this very sophisticated 1960s looking radio frequency detector, and they got all of this sort of buzz that looked like noise in the background, and they thought that something was up with their equipment, But actually, after a lot of investigation, they realized that what they were detecting was cosmic background radiation, the echo from the Big Bang. And in fact, you have also seen part of this cosmic background radiation, because a small percentage, if you remember the bad old days of television, where television was all analog, and if you tuned your TV out, you'd just get snow, right? There was no signal. So that snow that you get, the sort of fuzziness and the crackle, the static, so to speak, that is picking up partly cosmic background radiation. About 4 or 5% of it is actually cosmic background radiation. This is the echo of the Big Bang, this famous image that has recently been redone in a slightly greater resolution. And what you're actually looking at are patches of the universe which are beginning to coalesce into matter. And I'm going to show you a simulation of what it would have looked like if you were able to sort of take a God's eye view of the universe, from the Big Bang until the present day. Let's have a look at it right now. This is why I wanted the lights down a little bit. You can see that at the beginning, this is, there is no matter as such, okay? But as the universe develops, as it cools, what happens is that matter is able to begin to attract itself to one another, to other parts of matter, and coalesce to form what look like the beginnings of stars and structures in the galaxy. And as matter begins to clump together, okay, we find that those stars, planets, and all the rocky parts of the universe will begin to form. It's quite mesmerizing to look at it. But this is essentially how the universe began, obviously over a very long period of time. But ultimately, all of this was under the influence of gravity. Okay? Without gravity, matter wouldn't be able to coalesce into forming larger clumps of matter. Okay? So when you end up with larger areas like this, that will obviously draw more matter together, and so on and so on.
I thought that the experiments in spacecraft actually indicated that matter clumped together, not through gravity, but initially through attraction, electrostatic attraction.
I'm not quite sure where that's from, because the idea is that matter itself will attract to other matter automatically through gravity. Electrostatic attraction implies a charge of some sort. So I'm not quite sure where that idea came from, but let's move on. No, I think that the understanding is that it came through gravity. But there is an important addition to understanding this. Okay, here is the beginning of the Big Bang. Okay, whatever that is. You then have a period of rapid inflation, and this is what has been discovered very recently and has been proven as being real. Okay, and there's a lot of evidence for this rapid period of inflation, and this explains that the fact that the cosmos itself has a very sort of uniform appearance to it, right? And that's difficult to explain. After this period of inflation, you then get this afterglow pattern that you see over here, around 380,000 years. Okay, that's what we said before. From that moment onwards, this is when you get this sort of coalescing of matter into the stars and planets and galaxies and everything else. And over here, you have this is a picture of the spaceship that was able to image that thing over here, the sort of afterglow from the Big Bang. Okay? Now, this idea of inflation was proposed in the early 80s to explain some of the more difficult aspects of the Big Bang. Right? Why does space broadly look uniform from one end to the other? And the fact that there was a sort of very rapid expansion at the beginning would help to understand why space is very uniform across, the whole cosmos. Okay? If you look out wherever you look, you'll see a certain number of stars in a particular place. Why isn't it sort of more clumpy, or why is it so uniform like that? So this was one of the sort of ideas that scientists had, and in fact, this is recently been published. In fact, today this was published on most news outlets. This is from the BBC. This is a sort of a map of gravitational waves, which has a sort of characteristic twist in it, which implies that some of the theory about inflation is correct. Okay, we're not going to go into the physics of it, but ultimately it's very fascinating that the day that I am planning to give this talk, they come out with this sort of proof, so to speak, that inflation in fact is real, and it was obviously a very controversial theory, but it does help a lot to understand the actual nature of the cosmos itself. Okay. Now, the expansion of the universe appears to be uniform wherever you look. So if you're Edwin Hubble doing your experiments, you look out in one direction, you see galaxies moving away from you, look out in another direction, you see galaxies moving away. How does that work? Surely, if there was a Big Bang, there has to be a point where everything is expanding from. So if you look at this, if you imagine these are all separate galaxies or whatever, the expansion of the universe would sort of go like this. And you can see that if you're standing here in the middle, the expansion is uniform from all portions. However, what happens if you're standing here? Okay? If you're in a different place, if you're in a different solar system. Well, once again, the expansion is going to look uniform in all directions. You might be able to see different parts of the universe, but you'll be able to see it, no matter where you are, the expansion will always look uniform from whatever your position is. So that means, quite importantly, that the universe itself doesn't have a center as such. Okay? We can't think of it as a sort of sphere with a center, with a point that started, because wherever we are, we see it expanding uniformly. And that's because of a very important concept, which is that the Big Bang was not an explosion of matter. The Big Bang, the best way to think of it is a rapid expansion of space. Space being something that contains nothing. Okay? Matter came into existence at the same time, but the continued expansion of the universe is not an expansion of matter as such, it's an expansion of space. Okay. Now, what are the two biggest questions in cosmology? Well, I alluded to them before. Number one, we know that the universe came into existence through the Big Bang. Before this event, there was no matter, no space, and also no time. Okay? There was nothing. Scientists agree on that, except that they don't. But for the moment, they agree on that. Okay? They agree that the Big Bang started from a point of zero and created a rapid expansion of space, and with that came the existence of time. Okay? Before that, there could not be time because there was no space. Einstein showed that space and time are intrinsically linked together. Okay? So without space, there is no time, and without time, there's no space. So, the question is, what caused the Big Bang in the first place? Right? We have a Big Bang, but who lit the match is the famous way of people ask the question. Now, this sounds like a very banal question. You know, so what? Who lit the match? What does it matter? We don't know. We just know there was a Big Bang, and that's all we need to know about it. But the problem is, it's not so simple. Because we said before that the whole of science deals with the idea that there's a cause and effect, right? Something is an effect, it must have had a cause, it must have had a prior cause. But the Big Bang is the greatest effect of all, so what caused that? That's a very legitimate question. And in order to answer that question, we have to delve into some of the most fundamental areas of physics. And this is the classic response propagated by certain scientists as to what caused the Big Bang. How could it be that something came out of nothing? So what we're going to do is look at the best example of nothing that we have at the moment. Okay? And that is a vacuum state. A vacuum state means you take something, you evacuate all of the air and all of the particles in it and everything else, and you end up with a vacuum. There's nothing there. Okay? So if you look at this picture, these are stars. Okay, we don't get to see them very often, certainly not like this. But all of this black stuff in between them is all space. Right? There's nothing there. There's no matter. So let's take a little piece of that, or imagine we can take a little piece of that and analyze it to work out whether that could manifest something from nothing. That's the best example of nothing that we have. Okay. Now we all know that gravity works. You throw a ball up in the air, it reaches an apex, and it accelerates back to Earth. Okay? Gravity means that matter attracts other matter. That's what we said at the beginning, that when matter coalesced into the stars and planets and everything else, that's what was going on. So we've got a problem, because if the universe was created through gravity, through the fact that as there was this rapid expansion of space, matter attracted itself to other clumps of matter and all started clumping together, what we would expect is that eventually this expansion of the universe would slow down to a stop, okay? Because of gravity, because of the effects of gravity. Eventually, the effects of gravity will become so great that matter will begin to attract other matter from the universe, and everything will clump back together in what has been kindly termed the Big Crunch. Okay, so here is an explosion, okay, an explosion of different particles of matter. What we would expect eventually is that those particles of matter will coalesce back into that little point that they started from. And there are three models as to what's actually going to happen to the universe. Okay? This is the one that we would expect, a deceleration of the universe based on gravity, slowing everything down. So the universe would rapidly expand for a long period of time, and gravity would take over, and then eventually the universe would slow down until it stops, and eventually this line would continue all the way down and end up in a big crunch. Now, we could end up with a constant expansion, but that means that something has to be working against gravity in order to constantly expand the universe. Or, possibly, we could in fact end up with an accelerating universe, where there is another force at play that is helping to accelerate the expansion of the universe. Now, the beauty of these three models is that we can actually test what's going on. We can test what's going on by looking at the same things that Hubble looked at, but with far more sensitive telescopes and sensitive measuring equipment, and actually look to see whether the universe is expanding or not. Okay? Here is a graph of redshift against the observed magnitude. Okay? So what we're looking at here is a straight line would indicate a constantly accelerating universe. This area in pink would be a decelerating universe, and the area in blue would be an accelerating universe. And what scientists have discovered is, in fact, from this data, although it looks kind of like all over the place, but actually what they've discovered is the best fit of the current data that they have indicates that the universe is, in fact, expanding at an accelerating rate, which is very counterintuitive, but actually very helpful. Yes, your question?
So I'm bothered by gravity.
Sorry, say that again?
I'm bothered by gravity.
You're bothered by gravity?
We have, Earth has gravity.
Yes.
It's all the particles are sucking together, and that's what causes gravity.
Yes.
But other planets don't
Yes.
have gravity.
Of course they do. Of course they do.
Have their own-
Absolutely. Let me tell you this. You have a gravitational field. As being a human being and made therefore of matter, you have your own gravitational field. It's very weak, okay? But you actually have a gravitational field. And so if I took a ball, right, which also has a gravitational field, and I dropped it, obviously, boom, it would fall straight to Earth because of Earth's gigantic gravitational attraction. If I took that same ball and took another ball and got rid of every other piece of matter in the universe, and just had two balls and I set them at different ends of the universe, or I could do it with specks of dust, two tiny specks of dust, eventually those two specks of dust would attract to one another because of gravity. Okay?
That's because of gravity as opposed to an
Yeah, we're not talking about electrostatic attraction, okay? Because in fact, Electrostatic attraction is something slightly different. Just the very nature of matter gives it a gravitational field. Okay? So the Earth has a gravitational field that allows us to stick to it and not fly off into space. The Moon has a weaker gravitational field because it's smaller. That's why you see those nice pictures of the astronauts bouncing up and down on the Moon. Okay? They're not, you know...
Okay,
Huh?
sorry.
No, it's fine. No, it's good. It's good to explain things. Okay? Right.
So just to go further on that point, in
Yeah.
the gaps between
The gaps
stars,
between the stars, yeah.
what's happening there? Is there
Right.
gravity
Gravity,
there?
because that's why it
Or is
flows
it-
Right, well, there is the effect of the gravitational field from
The nearest,
planets and stars and
whatever.
everything. Well, everything, in fact. Gravitational fields extend for infinity. They just become very, very weak very quickly. So the Earth's gravitational field will have an effect on the Moon, and the Moon's gravitational field will have an effect on the Earth, and that's why there's a certain orbit, and we have, you know, the tidal system because of the Moon's gravitational pull, and so on and so forth. But in reality, those fields extend out ad infinitum into space. So eventually, that's why those two specks of dust will eventually attract one another, because their gravitational fields extend that far. Okay? But it's just because they're very small, it will take a long time. If you've got two very large bodies, then they will attract at a much faster rate. Okay? Now, why everything hasn't crunched together at the moment is because those effects haven't taken place. But over a very long, if you fast forward, you know, billions of years, what we would expect to see is all of matter eventually clumping together and attracting all other matter towards one central point in that big crunch. And that's not going to happen. And it's not happening, and thank God, and it's not happening because of something which is stopping that gravitational attraction. Something else is acting to push apart stars and planets and galaxies across the cosmos. And it's this mysterious force which scientists believe is associated with the empty space between the stars, which could be responsible for the Big Bang. Okay? Remember, the Big Bang, before the Big Bang, there was nothing. So we're going to take nothing and we're going to analyze nothing to find out if it could produce something. Okay?
That's right. With the big crunch,
Yes.
just prior to everything crunching together, is it not feasible that things will then repel and start this whole cycle again?
Possibly. Don't know. Don't know. Because the problem is that what started the Big Bang is not necessarily an expansion, well, we said it's not an expansion of matter as such. It's something else. So, I'm not sure. I think the answer is probably no. I'm not sure if scientists really have a handle on what would happen after that, because what you would need in order to return the universe to its sort of post-Big Bang state is enormous amounts of heat, where matter breaks down into, you know, subatomic particles. I'm not sure if that's what they're predicting. I'm not sure what they're predicting, actually, with the Big Crunch. But it's actually not that interesting anymore, because it's apparently not going to happen. Okay? Apparently what's going to happen is that the universe is going to continue expanding, which is good news. But the question then is, in fact, there was a Nobel Prize awarded to an individual who discovered this expansion. The problem, though, is what is expanding the universe? If there's something, if gravity is supposed to bring everything together and coalesce all this matter into something small, what is pushing it apart? There must be some other force acting to push it apart, right? Yeah, so that's the question we need to answer. Okay, so let's look at quantum theory, and I'm going to give you an introduction to quantum theory. I will start by saying, or paraphrasing, one of the most famous quantum physicists, Professor Richard Feynman, by saying that, don't worry if you don't understand this, neither do we. Okay? Let's take a light bulb. Now, for the pedants among you, this would be a monochromatic light bulb, but we've just used a light bulb for the time being. And we have two slits, okay? And the light is going to go through these two slits. These, in fact, will be very small slits. And what's going to happen is that my clicker works. The light is obviously emanating out from this as light waves. And these waves are going to go through these two slits, okay? And as they go through these two slits, they're going to interfere with one another. And we create an interference pattern which will look something like this. Okay, this is an experiment. If I had the time, you know, I'd probably bring something along and show you this. This you can demonstrate quite easily in the laboratory. Okay, you can actually make it at home. If you have a laser pointer like this, you can actually rig it up to create an interference pattern which would look something like this. Okay, it's a very simple double slit experiment. Now, what we're going to do is replace our bulb with an electron gun, and it could actually be any source which produces particles. Okay? Now this electron gun is going to fire electrons at these slits, and for the time being I'm just going to cover over one of the slits here, and so it's going to fire these electrons at this slit like this. Okay? And this plate over here is going to pick up these electrons, and you can see it firing electrons at this plate over here. Now what would you expect to see? I'm kind of giving it away really. You'd expect to see a band representing this slit over here of the electrons that have all gone through this slit. Okay? Very simple. All good so far. However, what I'm going to do is I'm going to take the other slit away. And I've shown you this picture because I want you to imagine taking a bucket of sand and pouring it through these two slits that are open. Now what you'd expect to see are two piles of sand, right? That's what you expect to see. Okay, so let's go back to this. I've now got my two slits open, and by shooting these electrons out, I'm essentially pouring sand through these two slits onto this thing. So what would you expect to see? Two bands going along here. That's what we would expect to see. Okay, so the scientists ran this experiment, and as they were running along, what they found after running this experiment for a little while is this. Now that is very strange, because these are particles. These are not waves. Waves interfere with one another in the same way that if you take two stones and you drop them into a pond, right, the ripples will go out and they'll interfere with one another. Particles are not supposed to interfere with one another. And so this was a very strange result. So they thought, well, maybe what's happening is that as we're shooting these electrons out, they're interfering with one another. Okay? So we're going to do something very clever. We're going to put a little detector here and detect the electrons going through one slit. And not only that, but we're going to fire them one at a time. Okay? One at a time. And what we should tell is that we should detect 50% of them going through this slit and 50% of them going through this slit. Okay? So they put this little detector on, there it is, it's nicely recording, and they ran the experiment again. Exactly the same experiment. And you know what happened? They got that. Now, that's very strange, because this detector is not touching the equipment. It's not going anywhere near it. All we're doing is sensing which slit the electron has gone through. And for some reason, we've managed to change the results of the experiment without actually touching anything. All we're doing is observing which slits the electron's gone through. So the scientists were very clever, and they said, well, maybe the equipment's somehow interfering with the electrons going through these slits. So what we'll do is we'll run the experiment again. We'll keep the detector there, but what we're going to do is we're going to unplug it, okay? We're just going to unplug it at the wall. Don't tell the electrons, okay, that we're unplugging it at the wall. We're just going to unplug it, and we're going to then run the experiment again with the detector there, but we're not going to look at which slits the electrons are going through. So they ran the experiment again. There it goes. And this is what they end up with. Now that is very strange. And for that, they had almost no explanation. There are explanations, there are ways of understanding it, which I'll run through with you, but that is very bizarre. Because by simply observing which slits each electron was going through, scientists were able to change the results of the experiment. From this interference pattern, which was unexpected, to the two bands which were expected. So what on earth is going on? So there are a number of explanations for this, none particularly good, but I'll try and sort of explain. First of all, it appeared that these electrons were doing two things at once. They were acting on the one hand as particles, which is what they were. They were electrons, particles, electrons are particles. But on the other hand, they were also behaving like waves, okay? So, what's the explanation? So scientists sort of thought that maybe as the electron's coming out, it sort of like splits into two in some way, and it actually really goes through both slits. It interferes in some way with one another, and it comes, back together, and it appears as one electron on the detector. But in some way, there is some interference that's going on. Okay. The best explanation that they came up with is called the Copenhagen explanation, or in my humble opinion, it's the best explanation, which is as follows. As the electron comes out, we mustn't think of it as one electron. It's a subatomic particle, and so we must think of it as a probability wave, or a cloud perhaps, of, we don't really know where this electron actually is. So this electron, as it comes out of here, could be anywhere in this cloud. Okay? Obviously it's not a real cloud, we just don't know where the electron is. Without looking, there is a probability that that electron could be in all sorts of different places. And in fact, there's a probability that it goes through this slit, it goes through this slit, there's a probability that it skips over here somehow or down there. All probabilities are on the table, all possibilities are on the table, and each one has a probability associated with it. And because of this wave, this probability wave function, it's possible, therefore, for the electrons to interfere with one another. Now this is a very bizarre result. And there was a very famous scientist at the time called Erwin Schrödinger, who proposed the following experiments. He said, let's imagine that we have a radioactive source up here, okay, which is emitting individual, let's say, alpha particles, okay, and we have a detector over here, and this is linked to a lever with a hammer and a bottle of poison, okay, and we put this in a box with a cat. Mine chose a cat, I don't know, okay. Now what's going to happen is we're going to close this box up. So at any given point after closing this box up, we're not looking to see whether the cat is alive or dead. But at any given point, an alpha particle could be emitted from this radioactive source. This lever will drop, and the poison will open up, and the cat will die. Okay? So if that happens, there is, your evil poison and a dead cat. But the problem is that we're not looking. So just as in our experiment, when we weren't observing those electrons, they could either be going through slit A or slit B, so too in this experiment, the cat, even though it must only be either dead or alive, is considered to be in a state where it is neither dead or alive, or perhaps both dead and alive, depending on how you look at it. We don't know what's going on. Maybe the hammer's dropped, maybe the hammer hasn't dropped. Now obviously he didn't actually do this experiment, right? But the idea is that thinking about this makes you realise that how can a cat possibly be in two different states, both dead and alive? It can't be. It has to be either one or the other. But until you look, in that situation, we don't know what state that cat's in. And until we observe that it's either one or the other, it's in both states. Okay? So when we observed which slit the electrons are going through, that was when the whole probability equation collapsed, the wave function collapsed, and it went through one slit or the other. But before we observed it, it could have been through either, and that's why we ended up with an interference pattern. Now, quantum theory doesn't make any sense, okay? In fact, Niels Bohr said, he was one of the quantum physicists, the original quantum physicists. If we're not astonished by this, we haven't understood it. But it makes a very interesting point, okay? On the subatomic level, in terms of subatomic particles, they do not behave in the way that we think they should. Okay? And this is going to lead us into understanding what's going on in that vacuum state. Yes?
Yeah, you started off when you said we put something that detects where the electrons are going.
Yeah.
You also said that can't possibly interfere with what the electrons are going to do.
Yeah, it doesn't interfere.
And it does, well, apparently it does.
Well, it does in the sense that we're able to observe.
Well, how do you know that the observation hasn't actually affected?
Because what we do is we turn it off. We leave all the equipment there, and we turn off the equipment. So the physical presence of the equipment isn't affecting it, because if it was, by turning it off, we would still see the same result, and we don't. We see a different result, just by not having the equipment on. Yeah.
So, are you saying that it's just by observing that you're changing the,
Yes.
the nature of the...
Yes.
So some energy from the detector there's some energy fault from the detector to the
Possibly a gravitational attraction from the detector.
No, it doesn't make any sense. We can sit here all night trying to explain it. I promise you, the greatest physicists in the world know that it doesn't make any sense. Okay? And it doesn't make any sense. However, it does in a world where things can be in two places at once. Okay, that's fine. Then it makes sense. But it doesn't make sense to us because we can't be in two places at once. We think of the physical world as being a very simple world where things can either be in one place or the other. But a subatomic particle is slightly different. And in fact, I'll give you some other examples. Okay? Let's look at the idea of what nothing actually is. One of the, as I mentioned before, some of the physicists involved in this, Heisenberg was another physicist very much involved in quantum theory, and he developed what is known as the Heisenberg uncertainty principle. Okay? And the uncertainty principle is very important, and this is going to feature very heavily in explaining this magical force that appears to be accelerating the expansion of the universe. Okay? Every subatomic particle has velocity and it has position in space. Okay? So at any given time, we should be able to measure the velocity and we should be able to measure where that particle is. Okay? So here is a particle whizzing through space that has a certain velocity and it has a position at each point. Heisenberg said it is impossible to know with certainty both the velocity and the position of any given particle. Okay? So if we take an image of that particle as it's going past and try to work out how fast it's going and where it is, we will only be able to end up with part of the information. If you know how fast it's going, you don't know exactly where it was. If you know where it was, you can't measure how fast it's going. And this has been applied in a number of different areas. Now, this leads us to a startling observation. If we take Heisenberg's uncertainty principle, what it basically means is that that vacuum state, that space, that nothingness, can actually have zero energy for short periods of time, okay? But it can only have an average energy of zero over a long period of time. So it can't have zero energy for short periods. It has to have some sort of energy fluctuation, because if we were able to say that space itself had zero energy all of the time, then we would be breaking Heisenberg's uncertainty principle. What does this mean? It means that at certain points in a vacuum, there must be particles coming in and out of existence all of the time. According to quantum theory, that's absolutely fine. Particles can come in and out of existence. They're known as virtual particles. That doesn't mean they don't exist, but it means that these virtual particles are coming in and out of existence all the time. And this creates an energy fluctuation in this vacuum state. Now, when we measure the average energy, it all averages that to zero, which is fine. That's what we'd expect to see, b'gadol. But on an individual scale, these energy fluctuations actually mean that a vacuum state is far from simply something that contains nothing. If particles are coming in and out of existence all of the time, creating these energy fluctuations, which is what we need in order to satisfy Heisenberg's uncertainty principle, then it's not such a great logical leap to say that what happened at the point of the Big Bang was some quantum fluctuation, which is what these are, some quantum fluctuation that generated a rapid expansion of space. And in fact, this is what scientists believe happened before the Big Bang. There was some sort of fluctuation, okay, in these virtual particles that allowed for the rapid expansion of space, some sort of chain reaction that occurred at that time. Okay?
So could you also say what happened before those particles, those random particles, those virtual particles?
Yeah.
I mean, there's something before that then. Sorry.
Oh, so wait a minute. So I'm going to slog it all up in a minute, okay? I'm just telling you what the scientists are saying. I'm going to slog it all up, don't worry. We're going to get there. So what that does as well is explain this magical energy that is pushing all of these stars and galaxies and planets apart, despite the fact that there's gravity that should be pulling everything together. Remember, we said the universe is expanding at an accelerating rate? So what's accelerating the expansion of the universe? this latent energy that is part of the vacuum state. These particles, these virtual particles that come in and out of existence. Okay? That is what is expanding the universe at an accelerating rate and working against gravity. So, okay, this is known as dark energy. Yes?
In order for it to be zero energy, you've got to have positive and negative energy.
Yes.
I don't understand the concept.
Because what can happen is that these virtual particles can produce. You're right. In a zero state energy, we still have to satisfy Asimov's uncertainty principle, which means that there have to be energy fluctuations. But if that's true, we can also posit the idea that in a vacuum state, these virtual particles coming in and out of existence can actually have a positive energy. And the conclusion that scientists have come to is that this dark energy that's pushing apart stars and galaxies and everything else is a result of these virtual particles. So a vacuum state, having nothing there, in fact, is impossible. You can't just have nothing. Particles are coming in and out of existence all of the time on a quantum level.
Yeah, I understand that, but that would all be positive energy.
Yes, there has to be a net positive energy ultimately. Okay? That's why it's called dark energy. And that is pushing apart these stars and galaxies, right? Now, so explaining this very strange phenomenon, physicists developed now a framework of what we call quantum mechanical models of subatomic particles, which is known as quantum field theory. This was one of the areas in which Richard Feynman worked very closely, and the particles are treated as this sort of excited state underlying of an underlying physical field. Okay? So in other words, any particle, electron, a photon, or anything else, has a certain field associated with it, and that field is known as a quantum field, and a particle is simply an excitation in that field. That's all it is. So when that field becomes excited, that creates a particle at a particular point, and that particle can move around space. Okay? We don't have another shear after this, but if we did, there's another class that I give on what reality actually is, what physical matter is actually made of. Because when you actually get down to it, there's very little there. But this sort of plugs into this idea, but we don't have time for that this series, but maybe another time. Now, okay. I'm not going to go into the details of this, but essentially what this means is that these quantum fields exist all over the place, and as a result can produce particles almost at will. And these are these virtual particles that can come into existence. Okay? Right, let's look at the bottom paragraph. Quantum theory therefore predicts that empty space will contain a sea of virtual particles which come in and out of existence so quickly that they are impossible to measure. Space may look smooth, but there is no such thing as a perfect vacuum. Okay? So that black space that we see between the stars, in fact, contain these particles coming in and out of existence all the time. We can't measure them directly, but we know that they must be there. Now, interestingly, there has been some work looking at some of the subatomic particles that exist, for example, inside a proton. Okay, here is a classic model of an atom. You have a nucleus over here which contains protons and neutrons, the electrons whizzing around the outside, and inside a proton you have these very strange little creatures, these subatomic particles called quarks. And these are bound together, these little wiggly lines here are called gluons, okay, because they stick the quarks together. Now, interestingly, there was a piece of work shown at one of the previous Nobel Prize ceremonies, which this is a sort of representation from real data of what's going on inside a proton. Okay? These sort of blobs that are coming in and out of existence are gluons that are literally popping in and out of existence inside a proton that glue together the quarks inside that proton. Okay? It's a phenomenal piece of work, and it shows how these virtual particles can come in and out of existence all of the time. Okay? Just to give you an idea, the frame rate for that simulation is 1 × 10⁻24 frames per second. Okay? Just to give you an idea of how quickly this is actually happening. So, okay, that's just if you didn't know what 1 × 10⁻24 looks like, it's that. Okay, now Lawrence Krauss is a very fascinating individual. He is the sort of what I would call the American physicist equivalent of Richard Dawkins in terms of his sort of manner and demeanour in terms of dealing with religion. However, he proposed this idea, or he's one of the proponents of this idea, that the Big Bang was able to occur because of these quantum fluctuations. Okay? And this is the book that he wrote as a result of this idea. The problem is that we're going to deal with some of the problems of this. This is number one, the response. Well, this is the response to the question of why the Big Bang could have happened. So we understand now that there had to have been quantum fluctuations beforehand in that vacuum state for the Big Bang to have occurred. Right? That's number one. Number two, the other question that we have to answer is why there is this wonderful universe set up perfectly for life. And this is called the Goldilocks paradox. Goldilocks, of course, being that little girl who just found the porridge to be just right. So what is the issue? What is the Goldilocks paradox? Now we know that in physics there are a number of constants that appear to be very finely tuned to make sure that the universe can exist in the way that it does, which allows for life to exist. And in fact, not just life, but matter itself. Okay, matter only is able to come into being by the fact that there are a variety of physical constants that are tuned perfectly for that to happen. Now, in such a finely tuned universe, right, we would imagine that this has not happened by accident. Okay? Let's just give you a little example, just in case you've forgotten the story of Goldilocks. Right? The porridge was just right, the bed was just right, the chair was just right. So everything in the universe looks just right. It looks like a put-up job, as one scientist put it. Now I want you to imagine for a moment. Here we go. This is Sir Martin Rees. It's now Lord Rees. I had a very informative email correspondence with him. I actually wanted him to come and speak in Northwood. He wouldn't come and speak, but he sort of answered a lot of questions. He wrote a book called Just 6 Numbers, where he took 6 of these constants and explained them, and explained why they appear to be so finely tuned for the existence of the universe and the existence of life. Okay? This is loosely known as the anthropic principle. Okay? Let me give you some examples. And these are sort of larger examples, not just these sort of funny scientific constants. The right ingredients. A planet needs liquid water, an energy source, and chemical building blocks like carbon, oxygen, hydrogen, and nitrogen for life forms we are familiar with to thrive. And without that, there is no life.
As we know it.
We
know it.
As we know it, correct. We also need a proper crust on the Earth. Okay, we wouldn't be able to live on Jupiter because it's just gas, right? Also, there are various worlds where the world is molten. Okay, so luckily, Earth has a suitable crust that we're able to live on. Okay, we also need it to be the right temperature, so liquid water can actually exist. In fact, the nature of water itself. Okay, we could spend the whole evening talking about the fact that water, as it goes lower and lower in temperature, gets to a point where it freezes, but then it expands, and it becomes less dense as a solid, which is very unusual. But if it didn't do that, life wouldn't be able to exist. Okay, because if water was more dense as a solid, ice would sink to the bottom of the ocean, and life would not be sustained in the ocean. Okay, just one idea. Anyway, the fact that we have a moon, right, it stabilizes our climate. Okay, the way that the planet is tilted, all of the seasons. Okay, we have the right type of sun, the right star, which provides just the right amount of energy for life. Okay, if it was too hot, obviously, life wouldn't be able to exist. If it was too cold, similarly, life wouldn't be able to exist. The Earth's core itself protects us from deadly solar radiation because it creates a magnetic field which deflects a lot of the solar radiation and other cosmic radiation. Okay, that's when you get flares from the sun, you end up with these beautiful displays, the northern lights or the southern lights, as a result of that. The fact that we have some nice, very kind neighbours, Jupiter protects us, shields us from stellar bombardment. Okay? So we've got all the right ingredients to create life. What is this like? Okay? Here's a little diagram of where our Earth sits. This is the sort of comfort zone over here. If our sun was any bigger, we'd be, this would be too close. If it was any smaller, we'd be too far away, and so on. So what is this like? This means that the universe appears to be designed. It appears to have a creator. And to a scientist, obviously, that's anathema. That doesn't make any sense. So how could all of these sort of random events produce this wonderful universe in which we live? I want you to imagine what the problem looks like. Okay, this is an equation that tells you what your chances are of winning the national lottery, assuming that there are 49 different numbers. Okay, you need 6 of those numbers to be correct. You plug all your numbers into the equation, and this is what you get. Okay, just under 14 million, 1 in 14 million. Now, I want you to imagine that we print one lottery ticket. Okay, only one person buys a lottery ticket that week, and they run the lottery, and that one lottery ticket wins. That would be pretty cool, right? That would be pretty spooky. The fact that all of these physical constants and the way that the Earth is set up allows for life to exist in the way that it does is a little bit like printing one lottery ticket and that lottery ticket winning. Okay. That's what it looks like. Very strange. However, scientists have an answer to this. What they say is that, of course, our universe is set up perfectly for life. And the fact that we can observe it is simply a function of the fact that life exists and we exist. However, there's nothing special about our universe, because in fact, our universe is simply one of millions, billions, trillions perhaps, of an infinite number of universes. And although we might feel like there was one lottery ticket printed and we were the winning ticket, actually what happened was that all 13,983,816 tickets with every single combination, in fact, were printed. It's just we didn't see the other 13,983,815 of them because those universes all failed to produce life and observers to observe the fact that there was a universe there. So the fact that we exist is simply a function of the fact that, yeah, we had the winning ticket, but if you print every single ticket, every combination, one of them's bound to win. This is the idea of multiverse theory, okay? So essentially, I put this down, I'm not going to go through it all over again, but right, there you have it. So if any of you want the slides later, you'll understand what I'm saying. Now, this multiverse theory is a brilliant answer to the Goldilocks paradox, okay? What we now need to do is address those two issues. First of all, from a religious perspective, and then answer those two questions from a scientific perspective. You have a question?
Yeah.